All right, let's take a look at question number 2. Now we're dealing with a rotation, solid of rotation situation. For number 2, this solid right here, this region right here, bounded by these two curves on the x-axis, is rotated about the x-axis. Okay, so our direction of rotation is in the direction of the x-axis. So what does that mean? That means that all our variables are going to be x's. All right. Also, our limits of integration are going to be x equals a and x equals b. So let's go ahead and write down the formulas for this situation for solids of rotation. Now, you have two choices of formulas. First thing you want to pick that determines your selection is the axis of rotation. Where is it located? So this line right here is the axis of rotation, right? So what is the equation of that line? The x-axis can be written as, this is the same thing as writing y equals 0. Okay, y equals 0 in this case is going to be our rotational axis. Okay, so let's call it well, we're going to label the functions in a minute, but what you want to note is that the axis of rotation is beneath the top function, and in this situation they're basically equal. So let's go ahead and order them. The axis of rotation is beneath the region, so we have the function on the top. Let's call this function on the top, and then this is the function on the bottom right here. Let's make that a yes. That blue function on the bottom, and it also happens to be an axis of rotation. So we have the function, if the function on the top is greater than the function on the bottom, and the function on the bottom is greater than or equal to the axis of rotation, let's call it function A, then the following formula holds. Okay, if we have the situation, then you have the volume is going to be pi times the integral from x equals A to x equals B of the function on the top of x. Let me use a blue card here so we can color code what's going on. So function on the top is red, so minus the function on the top of x, okay, minus the axis of rotation. All right, let's call our axis of rotation a of x. Okay, so the function on the top minus a of x. This is the radius of the outer disk. Okay, so pi r square. Don't forget to square your radius. This is the radius right here. Minus the function at the bottom. Let's call that f sub b, function at the bottom of x, minus the axis of rotation function, again, a of x. Close that. Now this is the radius of the inner disk. In this case, our inner disk has a radius of 0, but that's okay. This is the formula for all cases. So minus the function on the bottom minus the axis of rotation function, the function for the equation of the line for the axis of rotation. We have to square it, right? It's pi r square, area of a circle. Okay, dx. Oh, wait a minute. Let me close my parentheses with squiggly bracket before I put dx there. So you close that dx. All right. So this is basically the formula for a rotation. The solid generated when you rotate a region about a of x. Okay, axis of rotation is a of x, and the two functions are above the axis of rotation. In this case, the bottom function happens to be the axis of rotation, but that's fine. Now, what if the axis of rotation is above the two functions? What will your formula look like? And then another thing I want you to note is that the direction of our rotation is along the axis. That's why we have x, 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 x. These all x's, all right? Now, if a, okay, if a is greater than or equal to the function on the top, and the function on the top is greater than the function on the bottom, our volume is going to be similar to this, but the only thing that's going to happen is that these two quantities switch and the order of the terms in the parentheses switch also, okay? So it's going to be integral from x equals a to x equals b, squiggly bracket. I'm going to take this one and switch it around, so it's going to be the axis of rotation function, a of x, minus the function on the bottom of x, close that, square. This now is the area, oh snap, my pi, I put pi there, pi r square. This is the area of my outer disk, okay? Now we need the area of an inner disk, so minus parentheses a of x. That is the equation of the axis of rotation minus the function on the top. Okay, this one is much closer to the axis of rotation now because the axis of rotation is right above the function on the top, right? So x, and then you close that, quantity squared pi r square. There goes the area of the inner disk. So outer disk minus the inner disk gives you the area of the washer, okay? If there's no inner disk, you just have a disk. So that whole business, dx. So these are the two formulas for solids, volume of solids of revolution in the direction of the x-axis. That's why we'll have x's here. If it's in the y-axis, you just change your x's with y and basically the same thing, okay? So remember, this is the top, this is the bottom, this is the top, this is the bottom. All right, if you're going in the direction of the x-axis, this would be your top and this would be your bottom. All right, now let's go ahead and apply this formula to this problem that we're doing. So what's going to make this problem a little bit complicated, doing it up and down, is that we have two regions. What does it mean if we have two regions? We have two regions like we did in number one because the bottom function switches at 2. So we have to use this formula twice. We use this formula for the first region, and then we use the formula for the second region, solely generated by rotating each region, okay? So we're going to find out the volume when you rotate region 1 about the x-axis, and then region 2 about the x-axis also. All right? Okay, so let's split it down the center. And in order to avoid getting confused, we're just going to list everything for each region, and then we just pull it together in the formula, okay? All right, so let's go ahead and do it. So for region 1, let's see, region 1, what do we need? Well, first of all, which of these formulas are we using for this situation? Since the axis of rotation is beneath the upper function and happens to overlap the bottom function, we're going to be using the first formula, okay? So formula number 1. All right, so let's go ahead. Limits of integration for region 1, we're going from x, change this. Our lower limit of integration is going to be from x equals 0 all the way to x equals what? Let's see, from x equals 0 to x equals 2. All right, so we have the limits, and then we also need the function on the top. Function on the top in terms of x is our radical function root x, and then the function at the bottom for region 1 in terms of x again is simply 0, is that horizontal line y equals 0, and then the function for the axis of rotation a of x is also the x-axis, which is equal to 0. Is that all we need? Let's see. Yeah, that's all we need for region 1. So we're going to use this, apply this to the formula for region 1, and then we're going to apply the formula again to the components for region 2. So for region 2, we have the limits of integration goes from x equals 2 all the way to x equals 4. The function on the top stays the same. Please keep track of your variables here, okay? So this is going to be root x, and then the function at the bottom now switches. What does it switch to? As we did in number 1, the function on the bottom is now this linear function right here. This is y equals, let's change that, f b of x equals x minus 2. And then the top one, we know it's the radical function. I'm doing a lot of writing here so that I don't get confused with my x's and my y's, okay? Alright, so we have that. So function on the bottom in terms of x is equal to x minus 0. Is that it? Well, yeah, technically. Well, let's just write down the axis of rotation again, even though it's the same as the first one, 0. Okay, I think that's everything we need. We're just going to pull it together and apply it to the formula, and that should give us the volume, all right? So volume is going to be the combined integral. So for the first region, rotated about the x-axis will be the integral from 0 to 2. And then we have squiggly bracket, the function on the top is root x minus the axis of rotation, which is 0. Let's close that. What are we to do now? This is the radius. What do you do? Pi r what? Pi r squared. So don't forget that. Minus the function on the top. Wait a minute. Let's see. Function on the bottom. Function on the bottom here is 0. Minus the axis of rotation, which is also 0. So this is the radius. What's the radius? Is 0, right? And then so pi r squared dx. So what this is telling us is that there's only going to be a disk. You're not having a washer here because the second region is basically has 0 area. Okay, so you can drop this piece and then have the square root of x squared, and that will give you the volume of the solid generated by rotating region 1 about the x-axis. So that's that. Plus, remember, we're just setting it up. You can simplify it. I have tutorials, a lot of tutorials on how to do this, so you can take a look at my website and access that. So for the second region, same story, plus pi times the integral from a to b is from 2 to 4 of squiggly bracket, the function on the top is still the same function with x minus the function on the bottom. I'm sorry, minus the axis of rotation, okay? Minus the axis of rotation, which is 0. Quantity square minus the function on the bottom. Function on the bottom has now changed to x minus 2. For some reason I put x minus 0 here. It's x minus 2. So we have x minus 2 minus the axis of rotation, which is 0. Quantity squared equals that dx. Okay, so pi r squared, this is a big radius, and then pi r squared, this is a small radius. Okay, so this is the outer disk, this is the inner smaller disk, and then when you subtract them, you have the washer. If you look at your region right here, you notice that if you rotate this, you do not have any space in between. It's not hollow. Okay, it's like a filled paraboloid. And then this one, you have a big hollow region in there because you have a lower function, bottom function that's not the x-axis. So this is basically the expression to find the volume for the region when rotated about the, let's see, we're rotated about the line, about the x-axis. Okay? Alright, now let's take a look at the next one, problem number 3. Okay, let's write this down. Let's indicate this is number 2. This is question 2.